This is a San Francisco Big Analytics. Today, we invite NVIDIA's team to give a talk on how to accelerating Spark ML. So using RAPID. The first speaker is Eric. There is an echo sound somehow. Eric is the senior manager for the Spark ML team for NVIDIA. So we'll let him to introduce the other speakers, Jin-Feng Li, and while his talk. So with that, I'll turn to Eric.
Okay, thank you, Chester. Looks like only one of us can be unmuted here. We're going to get an echo. So so today we're going to be telling you folks about our recent work and an open source library that was just released to bring GPU acceleration to Spark, Apache Spark machine learning. And with me here today is my co-speaker and co-worker on this project, Jin-Feng, who's right here next to me physically. And other folks on the project from NVIDIA are Bobby Wang and Li Yang. This is joint work with them. Okay. So diving right in, we're going to go through a kind of a brief introduction and motivation for the work, and then we'll dive into sort of describing what we've done. So as we all know, requirements for data processing have been growing at a massive scale and continue to do so, and will for the foreseeable future. Fortunately, the big data tech stack has been able to keep up with these requirements through some key innovations like Hadoop coming online, open sourcing in the 2000 timeframe, and Apache Spark then following on about a decade or so later, introducing essentially a step function in its ability to keep up with these data processing requirements by kind of better utilizing CPU cores and memory. And most recently, we've got kind of another, what we feel is another step function in keeping up with these requirements, and that is around GPU accelerated Spark. And sort of the key event or sort of innovation that has enabled this, what we're kind of in the early phases of, is the addition of or incorporation of GPUs as a schedulable resource into Spark itself. And that's made it a lot easier to and a lot more reliable to deploy both third-party libraries for things like doing deep learning within Spark clusters, but also to accelerate Spark itself. And that's what we're going to be focusing on in this talk. So let's take a look at, let's review the main components of Apache Spark. So we've got the Spark core, which is the sort of the key plumbing providing the RDD API and all the networking and compute and serialization capabilities to enable massive processing of RDDs and data from distributed stores and etc. Then on top of those are these extensions. First, starting from the left, being a Spark SQL data frame API for doing extraction, transfer, and loading tasks. And then we've got Spark machine learning for doing distributed large-scale machine learning on that ETL data. And then we also have Spark streaming, or what's now called structured streaming, for doing low latency data ingestion and processing. And then there's GraphX for doing massive scale graph processing. So in terms of the focus of GPU acceleration to date, as far as Spark itself goes, it's been on these two components. And the Spark ML side is the topic of this talk. But there's actually been a fair amount of work that kind of kicked off with the sort of that step function around when GPU was added as a formal resource around accelerating ETL. And folks might not be that familiar with this. It's sort of you could say a non-traditional application of GPUs to accelerate these kinds of workloads. So I'm going to spend just one slide kind of recapping what's been done here. So there's this open source project. It launched almost around that time when GPUs were prioritized in Spark, called RAPIDS Accelerator for Apache Spark. And here's a link to the GitHub project. And essentially it provides GPU acceleration for Spark SQL and the data frames API. And it's built upon some other NVIDIA libraries for accelerating sort of sorts, group bys, these kinds of computational steps that are key to SQL, called RAPIDS cuDF. And it leverages that and then contributes all of the sort of integration that you need to go from that sort of capability, sort of single GPU capability, to being able to apply this to massive Spark distributed workloads. One of the key innovations in or sort of key features of the RAPIDS Accelerator for Apache Spark is that it works completely transparently to the user and the user's code. It requires no code change whatsoever. And in certain cases, and this is becoming less and less typical, there might not be sort of GPU accelerated capability for a certain step. In that case, the accelerator falls back seamlessly to CPU. And as I said, more and more of functionality has been migrated to GPU acceleration so that occurs less and less. But it is a huge convenience and a massive sort of enabler for adoption. So in terms of the benefits provided for ETL tasks, they're truly impressive. So these are runtime, cost savings, and power savings comparisons of CPU Spark SQL versus the GPU accelerated with the much lower numbers, looking at speed ups well over 5x, close to 6x, cost savings 4.5x, 5x efficiency in terms of power consumption. So these are obtained on a benchmark data set that sort of is based on industry standard benchmarks and has a bunch of highly relevant, sort of typical massive SQL queries. So it's a fairly realistic benchmark in terms of sort of actual workloads out there in the wild. Here are some links. Once these slides are posted, you can kind of explore those to additional blog posts and a GTC talk for more details on this. Of course, you can also check out the repo. So moving back to the ML side of things, what the topic of this talk. So just quickly recapping, Spark ML, as most of you probably are familiar, is a key part of Apache Spark. And it provides distributed implementations of many sort of along the lines of classical ML algorithms. But since its inception hasn't really been looked at from a GPU acceleration point of view. So out of the box, they're CP only. And Spark ML includes a bunch of other functionality around sort of the core algorithm implementations, things like ML pipelines, cross-validation, and various pre-processing functions to sort of enable end-to-end, batch machine learning from pre-processing to training to inference, all within Spark. So this brings us to the main contribution and novelty in this talk, which is what we're calling Spark RAPIDS ML. And that's a new library that we've just open sourced a couple months back. There's the GitHub link, and it provides a Python there's an API, essentially, targeting the PySpark ML data frame API to accelerate Spark ML. So with that, let's kind of step back a little bit and see what once we kind of take the ETL side of things and this newer library, Spark RAPIDS ML. This is kind of the picture that we have, which is sort of the stack that provides end-to-end acceleration, both on the ETL side, and once that data's been ETL'd, either in a data frame form or perhaps persisted to a distributed store, we've got on the ML side our new library to pick things up on the ML training and inference side. And as I had kind of briefly alluded to before, both of these libraries are heavily leveraging NVIDIA's RAPIDS suite of GPU accelerated algorithms for data frame type processing, leveraged by the ETL side, as well as machine learning type processing that we'll say more about, that we leverage on the Spark RAPIDS ML side. And of course, sitting under all of this is NVIDIA's GPU accelerated infrastructure and the whole CUDA stack, enabling leveraging all of that. So that's kind of the combined picture at this point. So coming back to Spark RAPIDS ML, we've kicked things off with the following initially supported algorithms. So we've got k-means, PCA, linear regression with different types of regularization, and random forest classification and regression. And all of these have counterparts in Spark ML, of course. And while this is sort of our initial list of algorithms, we're certainly planning to expand this and cover more of what's in Spark ML. One other thing we did with this initial release is include an algorithm that is not in Spark ML. And this is distributed GPU accelerated k-nearest neighbors. And there is actually something somewhat similar in Spark ML, locality sensitive hashing. And that's actually the class there that in parentheses. And we've implemented this with a similar API. And why did we include this algorithm? You'll learn more about sort of our architecture, but it was kind of low-hanging fruit given our overall approach, leveraging the existing RAPIDS libraries, which had a distributed implementation of this. And then given all the excitement around all the different ways of embedding images, text, etc., through large language models, and just the sort of ever-growing relevance of large-scale vector processing. This seemed like a good thing to kind of have out of the gate. So in terms of key objectives for sort of as we set out to build this library, we have the following. So around API, we sort of made a strong point and requirement to be fully compatible with the PySpark data frame style API, and specifically requiring no application code change, and just for the time being, a package import change. In terms of speed up and cost benefits, drawing a page from the ETL acceleration side of things, obviously we wanted to demonstrate significant CPU improvement over PySpark CPU, both in speed up and cost savings. And then, as I've kind of alluded to a few times, we certainly wanted to leverage existing capabilities around accelerating ML in NVIDIA, and specifically the NVIDIA RAPIDS cuML library. So with that, I'm going to kind of take a deeper dive into, or Jinfeng and I, into each of these 3 bullets. And we'll start off with the API. So with the API objective, as I mentioned, we set out to be super compatible, no code change with existing PySpark ML's API. So here's a snippet of k-means. We've got
sorry, Eric, can I interrupt for a second?
Estimator, setting some parameters, the number of vectors in the number of clusters, the feature column, how many iterations, etc. And then we invoke the fit method on the estimator on some data frame, get a model, we can save the model, persist it, and then we can also transform, that same data set or some other data set to find the, sort of the nearest centroids. So in terms of sort of the API compatibility for Spark Rapids ML, you can see that this is what we're offering. So everything stays the same, just a package import changes at the very top, and you have GPU accelerated k-means. So that's what we set out to achieve with all of those algorithms that I had listed. And what are the benefits of this? So for one thing, Spark devs hope, looking to leverage this new library don't need to learn a new API. They can just, go with what they're familiar with. It should make it quite a bit easier to migrate existing applications, which we're hoping will be a significant use case for this. So for example, if an application is leveraging things like ML pipelines, cross-validator, with this API compatibility, that code can continue to leverage all of those pieces without having to sort of refactor or rewrite that part. And yeah, so that's why we kind of set out to meet this objective. So moving on to the performance objective, how are we doing on time? We're good? Okay. I'll show some results, some benchmarking results for those algorithms that I had listed that we support and are also in Spark ML CPU version. So for the benchmarking, in terms of the workload and the data, what are we benchmarking? We're benchmarking the fit method on the estimators, i.e. the training step. And this is the by far the more computationally intensive of the fit transform methods. The benchmark involves reading a data frame that's been stored in Parquet format in AWS S3 bucket. The workloads were chosen to be pretty compute intensive. So although not like, massive scale for this particular benchmark. So we've got 1 million rows and 3,000 dimensional vectors. And as I mentioned, the data is available currently in an S3 public bucket. And that's done so that folks can come in. They have an AWS account. They can try this out. Okay. So the environment for the benchmark was Databricks, AWS hosted Spark. And this in particular demonstrates that, we can actually run this library on, the cloud platforms out there. And we'll say more about that later as well. And in the benchmark, we've got 3 node clusters. So not massive, but enough to demonstrate that we're doing, distributed computation with 2 executors, 1 driver, and then these are the specs and node types used for the respective clusters, CPU cluster and the GPU cluster. So the GPU cluster is pretty much the CPU cluster plus an A10 GPU in each of the nodes. Okay, so this link will take you to a part in our repo with instructions on how to reproduce the benchmarking, the results for which I'm going to show you the next few slides. And 1 level up from there, you will find instructions for running benchmarks in GCP Dataproc as well as AWS Elastic MapReduce.
Does this work in Databricks too?
So for this particular choice of workload, these are the running times that we obtain for the respective algorithms currently supported. So you can see that we're seeing quite a bit of speed up. So the y-axis is log scale, first of all. So if we look at k-means, we see that the CPU cluster took over 9,000 seconds, while the GPU cluster took 82 for the same workload with the same parameters. And then going across the other algorithms, a bit less speed up for PCA, linear regression, et cetera. And then coming back to random forest, the speed up factor bumps up. So part of this has to do with sort of the ratio of compute to I/O. So algorithms like k-means, you have quite a bit more compute happening in terms of the I/O overhead of getting data in and out of the GPU. And then for the other algorithms, that there's sort of less heavily compute intensive, but enough to see some pretty substantial gains. Now, you might recall that we did choose 3,000 dimensional vectors here. And naturally, as you would reduce that 3,000 to 1,000 to 300, depending on the use case, you're going to get a reduction in the overall speed up time. And whether, you have to check and test this on your particular workload to see if what kind of speed up you're going to get. That said, vector dimensions in the thousands are becoming increasingly common with the various embedding models out there as well as use cases in genomics, et cetera. So it's not a completely far-fetched hypothetical regime here that we're looking at. So going to cost benefits. By the way, the brown bars here are showing the speed up, just the ratios of those CPU runtime to GPU runtime, while the lighter tan bars are showing what we call the cost benefits. So the way those ratios are computed is we look at the runtimes for the respective clusters and multiply those by the costs per hour per second for the clusters. So naturally, the GPU cluster is going to cost a little more per unit time. However, you can see that all of these cost factors, so the cost factors are the ratio of the CPU cluster cost to the GPU cluster cost. They're all greater than 1, quite a bit greater than 1. In some cases, significantly greater. So what's going on here is that although the GPU cluster costs more because of the massive reduction in runtime, we get a net pretty significant reduction in cost. And this sort of echoes what we saw with the RAPIDS accelerator for Spark benefits on that first slide. So with that, I'm going to turn it over to Jinfeng, who's going to dive into the architecture, talk about usage, and time permitting, go through a demo notebook.
Do we want to ask questions first?
Sure, we can pause for questions.
Okay.
I think Ian was referring to me, just asking questions.
Anya, you want to say something?
Yeah, can you hear me?
Yes.
Oh, awesome. Yeah, Ian was referring to me asking questions earlier about does this run on Databricks? And in the slides, the link was shared. Here's the benchmark running on Databricks. So that question was answered. I think there were a couple more questions. How is power measured? And what does CU stand for in CUDA? And another
CU, yeah, there's one question to say, what's the CU stands for? It's a CUDA, right?
CUDA, yeah.
And does Spark Rapids require NVIDIA GPUs to run, or can it run on any hardware?
It requires NVIDIA GPUs, specifically CUDA as well. It's all built on that stack.
Nice. Okay, so I think that is all the questions that were in the text in the chat.
Anya, why don't you just ask the question, because I have echo sounds, but we're in the same room, so
I can turn off my microphone.
yeah, we can ask Anya to repeat the question to ask.
Okay, yeah. As the questions come in the chat, I can repeat them. Yeah, I think that's all the questions that came up so far.
Yeah, there's a quick question. See, how do you measure the power?
So that, I guess that's referring to the ETL slide, since we didn't have power measurements for our portion, for the ML portion. And that's actually a good question. I think they use some tools.
Yeah. Maybe I could answer that question.
Provide for measuring power across some workload. But if you want to know more, we can refer you to the ETL project folks. They can tell you more.
Can you guys hear me?
Whoever asked that question.
Yeah, we're going to invite the team.
It sounds like Andy Feng has an answer. Can you guys hear Andy?
Okay.
Yeah. Can you guys hear me? This is Andy here.
Yeah.
So what we measured was so that particular thing. So we did not was for the power side particular numbers was not measured on CSP directly. What we did was did a measurement in our on-prem cluster, right? Also, so on-prem clusters, we have a set of the their servers. For the their servers, there was a mechanism you could measure, like before you do the job, right? You could say, okay, let's set is the how much power I have consumed for each individual node. You could try to measure for a given workload, how much power was consumed. So in this case, like we have multiple nodes, right, for the ETL. So then we just add them up. So that was give us the, the estimated power consumption. And, it's kind of the estimate. It's based for we look in the CSP configurations, then we have local node, we did that measurement, and we estimated CSP should be having similar power consumption. But as Eric said, I think we were happy to take offline. We see this is the power consumption side of the things and the carbon footprint as an important interest for some of our customers.
Great, thank you, Andy. So before Jun-Feng, there's one more question related to say, hey, there's one slide, so no code changes. What that means is that to simply start the GPU in the Databricks and then things just happen. And there's some configuration you do need to set it up for the ETL side.
Oh, for the ETL side?
Well, for the Spark side, you already showed that you need to change the import, right?
Yeah.
Yeah, for the ETL side.
Yeah, for the ETL side, there's no code change whatsoever, including because we are talking about the Spark SQL, Spark data frame, right? So there's even no imported statement change. The only thing you need to do is when you launch your Spark job, you're going to configure to use all plugins. Again, please check out the details from our GitHub.
Great, great. I think I answered almost all, I think all the questions. So Jun-Feng, please continue.
Yeah, so I'll mute myself.
Yeah.
Okay. Yeah, Eric, so I need you to help me. Yeah, so slides. The Spark RAPIDS ML mainly leverage RAPIDS QML for the compute. And the QML project is a suite for fast GPU accelerated machine learning algorithms. And its key objective is to provide a Python APIs that match the scikit-learn API that runs 10x to 50x faster with the GPU acceleration. And the back end of QML is in C++, and it also leverage CUDA NICO communication for the best efficiency. And the QML project provides a list of algorithms that support multi-node, multi-GPU. It provides the efficient communication, the GPU accelerated communication using NICO, and it supports PCI and infinite band hardware. For the distributed execution, the QML mainly use Dask API. This table shows the list of algorithms currently provided in QML. These algorithms include unsupervised algorithms, including clustering, dimensionality reduction, and nearest neighbors. And these algorithms also include supervised algorithms, including linear models and nonlinear models. The link on the left bottom is the QML repository on GitHub. And these slides show how our repository connect PySpark API with the QML C++ compute backend. So Spark RAPIDS ML leverage PySpark CPU API to get the algorithm parameters and the CPU data sets. And Spark RAPIDS ML will create wrappers of the QML multi-GPU class and NICO communication layer. And to connect the PySpark's API and the QML backend, Spark RAPIDS ML leverage PySpark APIs, including repartition, map impetus, and barrier to set up the multi-GPU clusters and the NICO communicator. This snippet shows an example of k-means. So when the user call FIG on a CPU data set, the Spark RAPIDS ML will map the algorithm parameter, Spark algorithm parameter to QML algorithm parameters. And the next will call repartition on the CPU data frame to partition your data set into the number of GPUs. And the next step will leverage map impedance and the barrier to make sure all the tasks can finish at the same time. And inside this chain UDF functor, the main computation happens. So this chain UDF functor, we are taking a CPU data frame, and we need to convert it into the QML data type. One type is to a NumPy array. And then we will leverage PySpark barrier context API to initialize NICO communication. And after the data set and the communication are ready, we call the QML multi-GPU class, the FIG, on these NumPy arrays to get the model. And this slide shows the class hierarchy. And the GPU class mainly extends the next. Yeah, so the GPU class mainly extends the PySpark CPU class, including estimator and model, in order to be compatible with other pipelines, CPU pipelines. And the GPU class will automatically map the PySpark algorithm parameters to QML algorithm parameters. And also the GPU class will support estimator and model persistence to disk. The key GPU compute happen inside this FIG function of the QML estimator. Inside this FIG function, the Spark QML, Spark RAPIDS ML will handle the dataset preparation and the parameter mapping validation and the GPU scheduling, and also initialize the QML context for communication. And similarly, so for the main GPU compute in transform of the model class also deal with this data preparation, communication, and calling QML C++ backend. Yeah, so next I'm going to present how to use the Spark RAPIDS ML. This slide shows how to install the Spark RAPIDS ML. So we have dependencies to the RAPIDS ML. So the user needs to install the RAPIDS dependencies. User can use the conda install in one command line, or the pip install also in one command line. And after the RAPIDS dependency is installed, then the user can install the Spark RAPIDS ML using the pip install command. And remember to activate your conda environment if you adopt conda when installing RAPIDS dependency. So after installation, then user can submit a PySpark job to a cluster. So the submit command is basically the same as the CPU submit command, except that the user needs to specify 4 GPU-related configurations. The first configuration will assign one whole GPU to one task. This is required by the NICO communication layer. And the second configuration will specify the number of GPUs to one executor. This can be set to the number of GPUs in a machine, assuming that one machine has one executor. And the last 2 configs, just copy and paste into your command. These are natively support since Spark 3.0 release. The purpose is to automatically discover GPU hardware in your cluster. Yeah, so I'm going to show a demo to run k-means code, GPU code in Databricks cluster. Can you open the... Thanks. Yeah, so this is a notebook snapshot. So in order to use GPU k-means, so we import the related Python package. As the first step, we created a synthetic data set. We use the scikit-learn dataset API to create a data set of 1 million rows and 500 columns. The next step will convert this scikit-learn dataset to a distributed Spark CPU data frame, leverage the Spark API create data frame. And so the next step will call a GPU class. So this function will build an estimator. It actually can accept both CPU class and GPU class. Once the class is passed in, this function will return an estimator object. And the CPU code will pass in the GPU code will pass in a GPU class to get a GPU estimator. And the GPU estimator support persistence to disk in the same way as a CPU estimator. And the next will directly call GPU estimator on a CPU data frame. This data frame will be automatically copied into GPU to finish the computation. On this synthetic data set, this fit will take 25 seconds. And the next, you can inspect some values in this estimator and inspect the model, such as the clusters. Once you get the GPU model class, you can use it on to transform a CPU data frame. Similarly, this CPU data frame will be copied to GPU to finish the transform process. Yeah, so the above are the GPU code. And the following will be the CPU code. I think going down. Yeah, so yeah, the CPU code will be similar, except we pass in the CPU class to get a CPU estimator, and we call fit on a CPU data frame as required by the PySpark PySpark ML, CPU ML mainly accept a vector data frame, so we need to convert the data type. After fitting, we have a CPU model. Then we are able to run this CPU model to transform the whole data set in a similar way. What is worth mentioning is that this CPU fit time on this synthetic data set took about 500 seconds. So recall that the GPU fit was 25 seconds. The speed up was around 20x on this synthetic data set of 1 million rows and 500 columns. Yeah, similarly, when the fit and transform are finished, you can inspect the final results and some of the model parameters.
Okay.
Yeah. So the takeaway is that the Spark RAPIDS ML have been made open source under Apache v2 license. It requires no application code change. And in order to use that, one single import statement is sufficient. In terms of performance, Spark RAPIDS ML shows 3 times to 50 times cost benefit. And it can be run on-prem and all the cloud service providers, including Databricks, Google Cloud, Dataproc, and Amazon AWS EMR. For more information, please visit our GitHub repository and our tech blog.
Thank you. Thank you for the great talk, and both Eric and Jim Fun. So I open to
Mute yourself.
yeah, some open the floor to questions. So I think I think one basic question people asking is, can you get the slides shared after this, and also the notebook, the demo? Is that possible?
Yeah.
Okay, so yeah, so we probably
The
post.
notebooks and demo instructions are available on the GitHub repository, and we will make the slides ready.
Okay, great. Yeah, so we'll share the link on the meetup page and afterwards, and so people can directly get it. Okay, so any other questions related to the details and the architecture related changes of Jim Feng just presented? Or general question to Eric?
Sorry, I joined late. I just joined a couple of minutes ago. Will be any recording available afterwards?
Yes, this is recorded. I'll share once I got the video upload to YouTube, and I'll share on the meetup page.
Okay, sounds good. Thanks. So okay.
Yeah, since we don't have a lot of people, so you can unmute yourself if you want to speak directly. Or if you don't want to speak, and you can just put your on the chat. Oh, I see. Anya actually has a question. He said, "Is what's the use cases are the best for the RAPIDS, and you know which are not so good, which is which data type is a not good fit?"
You're talking about RAPIDS ETs, the ETL part, or
I
Well,
guess
this question can focus on the ML side. So you showed us in the benchmark quite a few different types of machine learning models. So what makes them a good fit, or what would make another machine learning model not a good fit? Eric, we can't hear you.
is this better? Chester, mute.
Yes, that's better.
Okay, so I'd say that the key is sort of, hand-wavingly, the ratio of compute to IO. So the more compute intensive your algorithm is, the better candidate it would be. And that goes for parameter choices as well. So things like, k-means, if you have a data set with 5-dimensional vectors, that's not going to have as big a payoff in terms of GPU acceleration, in terms of the compute side sort of outweighing the cost of loading the data into the GPU. Similarly for the number of clusters, that kind of thing. So at this point, we don't have like a tool that will, given the parameters of your problem, tell you the benefits. We're sort of floating around ideas for that kind of thing. So the best we can say is to give it a try on your workload. But intuitively, the more compute to IO that's happening, the better off you're going to be with GPU acceleration. Now, on the ETL side of things, there's actually an open source tool called Spark RAPIDS qualification tool, something like that. It should be linked from, you should be able to get to it from the docs page for that library. And that will actually ingest event logs from Spark workloads and create an estimate of the benefits of using the RAPIDS accelerator for Spark library for that workload. So that's a really interesting thing. There's more and more functionality being added to that tool, including tuning your job. We hope to maybe get there for ML, but you know, it's early days for us. I don't know if that
Yeah, that's great.
answers
Thank
your
you.
question, or if you have follow-up.
Yeah, that's great. That answers my question. Thanks.
Annie, you have does that address your question?
Oh, I guess you guys can't hear me.
Sorry, I didn't get.
Eric, can you hear this? This is Rich Katz. I like the fact that you started out
She
with
says
the
the
three.
answer, yes.
Okay.
I like the fact that you started out with the 3 GPU model, because that's kind of the minimum to see the interaction between multiple GPUs. I think this is really well done. I really appreciate what you put together. Thank you very much. I've done this kind of work a long time ago, so I really appreciate it.
Thank you. That's really great feedback. Thank you very much.
Yeah, we can hear Richard. We've heard Richard.
I think Maddie had a question.
Go ahead.
Hey, thank you so much for putting it together. I think that it answered my question. Probably like the next steps for you guys is adding more models and like deep learning models.
So on the deep learning side, that's sort of a different track. What we're hoping, looking to do is fill out our list of, our coverage of Spark ML, which is focused more on classical ML models. So like, you know, for example, logistic regression, something that we don't have right now, and we need to add that. So, and then we're going to look at all the other algorithms. I don't know that we'll aim for 100% coverage. We'll try to get more insight into which of those algorithms, you know, beyond what we have now, and sort of the obvious ones folks would want to see. So we're counting on some user feedback to guide us there. But on the deep learning side, we have some other activities in our Spark team focused on that, but those would be different projects. We had, I don't know if I should digress into that, but Li Yang, one of our collaborators on this, he's also working on, you know, on improving DL usage within Spark clusters, and he recently had a contribution that came out in Spark 3.4 for improving batch, easing the process of going from a trained model to doing large scale batch inference in a Spark cluster. Yeah, I think it's called, there's a function added called predict batch UDF. You can look that up, just came out. And he's also had some contributions to Horovod Spark estimator. And yeah, but that's a different track from this work.
Maddie, I hope that
Thank you
answers
so
your
much.
question.
Yeah, thanks.
Okay, can you hear us? Does that address your question?
Yeah, yes, thank you so much. Yeah.
Okay, great. So with that, I think we come to the hour. So I want to thank the speaker, Eric and Jin Feng. And so I hope people try this project. Hope this is helpful. So we'll see you next time. Okay, bye-bye.